Hello and welcome to the STEMCstudio channel. In this video, which continues the geometric algebra in STEMCstudio series, we'll take a look at subtraction of multivectors. How do we subtract one multivector from another? We'll also take a look at our old addition operator overloading and addition method and see how we need to sort of fill it in to deal with the fact that we have now these multiple grade vectors within our multivector. That is the scalar, the vector parts, and the bivector parts. Okay, let's get started. So let's go and just clear the decks as we usually do. We'll just run the program. We'll hide our documentation, and what we want to do now is probably just get rid of the stuff that we've got on the diagram. Okay, except perhaps the E1 and E2 because they are such significant things to us. So we'll get rid of those. We've still got E1 and E2. And apparently we're not using our coords method right now. You know what we'll do is we're going to actually go and put that into another file all by itself. Now, this is something actually that I think we should have done anyway. What we want to do is we want to kind of like keep this main line of our project, which is the index.ts file, fairly short and fairly readable, and we want to sort of separate out different concerns into different modules. So it should be apparent that this coords method was used as a way to sort of bridge from our multivector to the JSX graph library. So I'm going to go with a name that I think suggests that, which is the JSX bridge. Okay, you know, you can name things, and then if you have a better idea later on, you can always rename them. So let's call this JSX bridge.ts. We'll create that file, and what I want to do is I want to go back to my index.ts, take this coords function, cut it out of there, and put it in the JSX bridge file. And of course, I will need to export this function in case I ever want to use it again. Okay, now the first thing that you'll see is there's an error. We cannot find our multivector class, and of course the multivector class is coming from its own file. So we're going to import from, and the file that it's coming from is the ./mult2d. And go back to here, control space bar, and it's the only thing there, so I can bring it in. This is probably a good time as well to actually just improve this file a little bit. G was the name of our old Gibbs thing, so I'm going to just rename this and maybe call it MV multivector. Okay, and if you want, you can go ahead and give this some kind of documentation. So it has a parameter which is called MV, and we're returning the coordinates corresponding. Actually, this thing really, in some ways, we should just call it a vector because that's kind of like what we're interested in. So it's a multivector, sure, that's the type, but we're really only interested in the vector components. The coordinates corresponding to the head of the, and what we really mean here is it's a position vector. In other words, it's a vector from the origin. So then the numbers x and y do become the coordinates. So it returns those. The vector is the position vector, and this is going to be computes the coordinates of the point that is identified by the position vector. Okay, computes the coordinates of the point that is identified by the position vector. So we have the parameter vector is the position vector. That's good. And it returns the coordinates corresponding to the head of the position vector. Something else that we can do actually to improve this a little bit more is, this is really just documentation, but you can actually put names in here like that. And now when you hover over elsewhere in the code, you'll see that X has been kind of like, we've labeled that first number in the array. So that's kind of quite nice. And I could add a little bit more documentation, and I should add a little bit more documentation to say that X corresponds to the X coefficient of the multivector. Okay, but anyway, we just preserved this function. I think it'll be useful to us later. We've gotten it out of our main line here. Okay, so let's create some generic multivector. Say we'll create one called A, and that's going to be a new multivector. And we're going to construct it from, say, these coefficients. Okay, say we don't really need B. Okay, and so there it is. Okay, so A is the scalar quantity 2 plus 3 in the E1 direction plus 5 in E2 direction plus 7 lots of the directed area, the unit directed area. Okay, so what we want to do now is we want to calculate, we want to let's go revisit our addition first. Okay, so I'm going to create another bivector. We'll call it just B, obviously, the natural thing to do. So B is, say, and I'm just going to use 1, 2, 3, 4. Will do, just to see something different. So there's B. Okay. And now let's just test our A plus B to see how that's working. So we're going to print that A plus B is A plus B. Okay. Just fit the format. So A plus B is 5. Well, the scalar part is clearly wrong, so we've got something we have to fill in there. The E1 part looks good. The E2 part is adding 5 plus 3 is 8. And the bivector part is not looking too good either. Okay, so let's go to addition and find out, to our unary operator for addition, and go and find out what's gone wrong here. So there's done the add, which adds the multivector on the right hand side, but it just delegates to this add method, right? So I can right click on that, go to the definition of it. There we go. And here it is, and you can see the problem immediately. I mean, we're just not doing anything with the scalar part, and we're not doing anything with the bivector part. Okay, so solution is pretty easy here. It's just this dot A plus the right hand side dot A is gonna fix the scalar part, and you can see it did. 2 plus 1 is 3. And then to fix the bivector part, just get the Explorer out of the way here, give ourselves a little bit more room. We just need to do this dot B plus the right hand side dot B. Okay. And that's kind of got it for us. I might have done something like this just to make things a little bit kind of like cleaner. Const A equals, and then I would go, oops, this dot A plus the right hand side dot A, and then I can just put A in here. The reason for doing this is that it's a kind of like a good template, if you like, because some of our some of our functions in future are actually going to get pretty darn complicated, and putting them all on a single line here is going to actually become kind of quite problematic. Okay, so let's just do that. And well, there's two more, so oops. So we need to do y. Is this dot y? Right hand side y. Dot b. It's dot b, and right hand side dot b, and then we have a, x, y, and b. Okay. Let that settle down, and then we'll just check our result. Now, you know, some people out there might be going, you know, why don't we have like good testing for this? We're gonna add automated testing at a point when our basic multivector class becomes kind of sort of a little bit more stable, so that we're not continually changing our testing all the time. So we will do that. Let's just do a quick check, the little desk check. 2 plus 1 is 3. Yep. 3 plus 2 is 5. 5, 3, 8. 7, 4, 11. So great. We've really kind of like completed our a plus b method, and that also then means that the a plus b operator overloading works. Okay, so what about subtraction? Let's do subtraction. So we'll just come back to our index file, and we want to put a minus sign in here just to indicate subtraction, and we need to have the operator overloading for subtraction. Of course, it's not defined. We haven't defined the subtraction operator yet, and so we get the not a number, because what's happened is that being unable to find that method, it's treated these just as if they were numbers, and when you add these two objects together, you get not a number. All right, so how are we going to fix that? Well, there's a kind of rather obvious way to fix it, which is just to kind of like say, you know, let's have a subtraction method, rather like the addition method, but we'll just put minus signs in the middle and we're all done, right? We could do that, and in fact, that turns out to be the correct answer in this case. But there is a slightly more formal way to do it that also helps us take a look a little bit more at operator overloading and the concept of a unary operator. So let's go and take a look at that. So I'm going to hide the code, bring back the documentation, and let's talk about the additive inverse first of a multivector. Okay, so this symbol here, minus a, is to be read as being kind of like a word in itself. It's like minus a, you know, say it quickly if you like. And, you know, that is the inverse of a. And the idea is that when we add to a, the inverse of a will get 0. Okay, so the question is, what exactly, how do we compute this inverse of a? Okay, now I think you'll probably immediately say, that's kind of easy. To get the 0 multivector, I just have to add to a something that looks like a, but all of the quantities have been converted to their negative. And that's absolutely true, and that's what we're going to do. So let's bring back our code. And what I'm going to do here, I'm going to say, okay, let's say that we'll go back a little bit here in our demo. And instead of trying to compute a minus b immediately, we're going to focus ourselves a little bit on the negative of a. Okay, so if a is that, then the inverse of a, or the additive inverse of a, because there are going to be many kinds of inverses. There can be inverses under multiplication, inverses under addition, that kind of thing. This is the additive inverse. And the way we're going to arrive at that is we're going to sort of look for a something that's like minus a, okay? Which is another operator that we need to implement, but this time it's called a unary operator because it only affects one thing after it. Now, what we're going to do is we're going to follow a process that's kind of pretty similar to what we've done before. And instead of first trying to do the operator overloading version, we're going to create a method, which I normally call .neg. Okay, and this is going to negate or change the signs of all of the components of A, and that's going to give us minus A. So let's go and implement that. Pretty easy. I can copy anything here. Let's just copy this one. That'll get, by copying, it'll get us kind of like most of what we need. So I want to implement neg. Oops, neg. Now it's a unary operator, so it doesn't take any arguments, because the only thing that we need is the multivector itself. So all we need to do is have minus this dot A, minus this dot X, minus this dot Y, and minus this dot B. Okay, and that goes away. I've been saying minus, that's kind of like not really, I guess, kind of quite accurate. It's sort of the negative sign in front of what is now just pure numbers, a bunch of pure numbers. And so you can see here that what's sort of happening is the sort of the unary minus, when applied to these numbers, is being sort of elevated or promoted into a sort of a unary minus that can act on the multivector. Okay. This dot B, it's, I think we're just not refreshing, yeah, the right time. So we've got a multivector, and all we've done is we've changed the signs of the individual components. Okay, so that's good. Now what we want to do is we want to build the unary minus version. So again, we need to know what the right method to overload is. So we go to operator overloading again. And if you look at the unary operators, the way we override minus is by implementing a double underscore neg method. Okay. Now there is actually a unary plus method, which in some ways it kind of like does nothing, but it actually does exist. So we could implement this too, just for completeness. All right, let's go back to our code here. And so what we need to implement is double underscore neg. So I suppose I should put it in here. Neg. It doesn't have any arguments, and it returns a multivector. And as before, we've already implemented it, so we're just going to say return this dot neg. Okay, and that should be sufficient for us to implement unary minus. So let's go and take a look at that. Run the code, hide the documentation. There is that. If I remove the neg, we should just get A. And then if I put a minus sign in front of it, you can see that it's negated all of the components. Again, you know, our implementation of toString is not very sophisticated at this point, and so we get this sort of slightly confusing plus minus. You should just in your mind's eye just realize that, you know, you could just like scratch out the pluses when you have the minus sign here. So it's -2, -3E1, -5E2. We can improve that obviously with improved formatting of our toString, and that'll be, well, maybe we'll do that as a short video in itself. Okay, so we've got unary minus. All right, so how do we get subtraction? So let's go back to our documentation here, and all we need to know is that subtraction of multivectors is just defined as adding to the thing on the left-hand side the unary minus version of the thing on the right-hand side, okay? And since the unary minus thing on the right-hand side was obtained just by changing its signs, we can kind of like do this in one step, okay? So let's give this a go. So let's go back to here. We want to start now talking again about subtraction. So we'll get rid of this. We'll bring back B. We're printing B. And we have to implement A minus B. Once again, I am going to I'm going to implement this through a method, and then we will add operator overloading. So the method we'll just call sub. It's going to be very much like add. Okay, and actually maybe what we can do is we can implement it initially based upon the definition. Let's see how we do with that, and then we can kind of like make a more performant version of it. So sub rst, we need to be put in about here. Sub will have a right-hand side, which is a multivector. It will return a multivector. Okay. And if we really play by the book, then this is really this dot add right-hand side dot neg. Okay. So, and we want to return that. Okay. So let's just do that. This dot add right hand side dot neg, and it doesn't look like we've gotten the right answer here. Or have we? Oh, yes, we have. 2 minus 1 is 1, 3 minus 2 is 1, 5 minus 3 is 2, and 7 minus 4 is 3. So in fact, we have achieved subtraction. But you could argue that this is not the most efficient way to do it, because what's happening here is when we call neg, we're creating a new multivector object, and then we pass that into the add, and then we create another new multivector object. And so it's kind of like a little bit wasteful. So what we can do is we can say, okay, this is the correct result. This is kind of what you get if you follow the sort of the math recipe. But what we want to do is we really just want to do it in one step, okay? So, this is something that happens in computing. You actually sometimes optimize things, and you follow the sort of the consequences of what would happen if I evaluated these things. Okay, so that's broken because we need to change all of these to minus signs. Okay, and now we've got A minus B, 2 minus 1, 3 minus 2 is 1, 5 minus 3, 7 minus 4, and we're all good. So we have implemented a sub method. Now what we want to do is we want to implement the operator overloading version so that we can change this and write A minus B instead of this sort of cumbersome A sub B logic, okay? So I'm going to tell you the method is called dunder sub, double underscore sub. So it's going to look a lot like the add. So I'm just going to copy that and stick it in the most appropriate place, which would probably be about here. And this is going to be called sub. So sub takes a multivector on the right-hand side, and internally it's going to call this dot sub. And we're good. We've got A minus B. All right. So I think that is everything that we set to do today. There is one other thing that I want to take a look at just to complete things a little bit. Well, maybe a couple of things since this is a short video. Okay, so let's say that we have the multivector, which is A is, let's say we have A is the multivector, as before it's like E1, or just like 2E1. Okay, so I'm kind of going back to my vectors again here, and B is the multivector like E1 plus 2 times E2. Okay, that should work, but what I'm interested in is actually A wedge B. Okay, so we're going to look at A wedge B. And you can see that, you know, that if you might remember it. Okay, I've got to use proper math jacks in here. A wedge B is that, okay, which is correct. And what I would like to do is I would like to divide this thing by, so I'm going to put it in parentheses, just to show that I'm trying to kind of like keep it all together. I would like to divide it by E1 wedge E2, and just to be kind of math jacksy, E1 wedge E underscore 2. Did I get that right? Yeah. Okay. So what I want to do is I want to take this quantity in here and divide it by E1 wedge E2. And the result should be 4. Okay, and we didn't get it. Did I? It looks like it's complaining about a parentheses there. There we go. Yeah, so that's what I'd like to happen. And of course, the result, since we know that A wedge B is actually 4 E1, E2, the result should give us a 4 in the scalar position. So we're coming back to our div, which we know at this point is kind of like a bit of a poor man's div, but that's okay. And we're just looking to make sure that we get a result when A wedge B is some multiple of the unit bivector here. So that bivector is the B part, and so what we're missing here is just a final term here for adding to A, the scalar part, the result, that divided by that. And if the right-hand side dot B, so easy to make mistakes, logic errors, there we go. And so A wedge B divided by E1 wedge E2 is the scalar, which is 4. And you can see it's got no vector components and it's got no bivector components. Okay, so I think that does it. We've got addition, subtraction. We've got unary minus. And we've completed or improved a little bit our poor man's division. Okay, so now at least we can kind of calculate the ratio of different bivectors. All right, so that does it. Fairly short and sweet video compared to some of the other videos, but this will help us a lot when we come to the next video. Where I would like to actually show you that even with what we've got right now, which is just the exterior product, we don't have any way to measure magnitudes of things or angles, so we can't give you the absolute magnitude of an area or the absolute length of a vector. We can't do those things yet, and yet we can actually compute and solve some problems. So that's what we're going to do in the next video, and then after that we'll progress again to completing our multivector. I hope you enjoyed this. If you liked it, hit the subscribe button. If you want to see more videos again, if you liked it and you want to share it with other people, let them know and hit the like button. Take care. Happy coding.